SwayamPrabha. Digital India. Educated India.
सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This will be lecture number 39, our ongoing series on mechanical measurements. In the last lecture, we have looked at the measurement of quantities using calorimetry. The next quantity of interest to us will be the measurement of viscosity of fluids, both liquids and gases. So what we will highlight in this lecture is to look at different techniques of measuring viscosity. The first one will be the use of laminar flow in a capillary tube, which can be used for both liquids as well as gases. The second one is a Seebold viscometer, which is useful for only liquids, and a rotating cylinder viscometer, which again is used for liquids. So we will try to understand the underlying principles as well as present examples to get an idea as to the kind of numbers which are involved in such apparatus. The laminar flow in a tube is taken as the model for the first method. Before we take a close look at the laminar tube flow, let us just digress a little bit, understand what viscosity is, just to get an idea as to what we are talking about. So this I will do by going to the board and giving the basis. So viscosity is a property just like thermal conductivity, which we have already considered earlier. Like thermal conductivity actually comes into picture when heat is conducted by or in the presence of a temperature field or temperature gradient. In the case of viscosity, there is because of a velocity gradient, there is a shear stress which is going to be generated in the fluid. So shear stress is the result, and the shear stress is due to a velocity gradient. And the thing to notice is that the velocity gradient and the shear stress are in perpendicular direction. What do I mean by that? Suppose I have velocity varying like this. So the velocity is varying like this. At any point, if I have, for example, so let us take the fluid above this. If we remove the fluid below this, because of the fluid below this, there is a stress which is going to, or a force of force which is due to shear, will appear as shown in this figure. So, the bottom layer of the fluid is going to decelerate or tends to pull back the top layer and vice versa. So, the shear stress is due to the velocity gradient. Actually, velocity gradient is this direction. In this case, the du by, let us say velocity is u, this is u, y is the direction in this particular direction, du by dy is the velocity gradient, and we can say that the shear stress tau is equal to some proportionality constant which we call as the dynamic viscosity multiplied by du by dy. Or if we want to look at viscosity, it will be the ratio of the shear stress in the fluid to the velocity gradient in the fluid. It may be either a liquid or a gas. So, the measurement of the viscosity will mean somehow we have to measure the shear stress, or the effect of the shear stress we have to measure. In the case of tube flow, the effect of the shear stress or the shear at the wall is to give rise to a pressure gradient in the direction of flow. So, the pressure reduces in the direction of flow, and the pressure can be easily measured because it is a scalar quantity, and we already know how to measure pressure by putting a manometer or attaching a manometer through a static hole. We can provide static hole along the length of the tube, and we can connect a manometer and measure the pressure drop very easily. Therefore, the shear stress is itself not directly measured, but it is the effect of the shear at the wall which gives rise to the pressure gradient along the direction of flow, the pressure drop along the direction of the flow which is measured, and therefore, the measurement of viscosity or the evaluation of viscosity or the estimation of viscosity is through the effect of viscosity, which is to create a pressure drop along the flow direction. So, with this background, let us go back to the slide which we were looking at earlier. I have taken a simple case of laminar tube flow. I am considering a cylindrical tube of some diameter d, and the fluid is entering. Let me refer to x equal to 0 as the entry to the tube. The fluid is coming from some tank or some source or some reservoir, and we will assume for the present that it is entering the tube with a uniform velocity as shown here. So, the velocity is uniform as shown here. As it moves through the tube, because of viscosity, the velocity of the fluid just in contact with the circular tube, which itself is stationary, the circular tube is stationary. Therefore, the velocity of the liquid or the fluid adjacent to the wall is also equal to 0, as you can see here. Before entry, of course, it is equal to the velocity, which is the average velocity, and as it enters the tube, the velocity at the wall becomes equal to 0. And what happens during the flow is indicated schematically here, and somewhat exaggerated because we want to show things clearly. You can see that at this particular section, x greater than 0, x equal to 0 is the entry point, x is slightly inside the tube, you can see that the velocity is 0 at the wall, and then it increases and becomes a maximum towards the center line. And you will also notice that because the fluid near the wall has been decelerated, it has become, the velocity has reduced. To keep continuity or to transport the same amount of volume, the flow in the center line, near the center line, accelerates. So, the flow is actually, the velocity is increasing in the core, this we call as the core, and near the wall, which we refer to as the boundary layer, the velocity is actually becoming smaller and smaller and eventually becomes 0 at the wall. So, this is the typical velocity profile you will measure if you are to make the measurement of velocity across the cross section here, and this velocity profile is given by u, which is a function both x and r. That means x is the location along the length of the pipe or the tube, and r is the radius measured in the radial direction in the tube. So, it depends on two coordinates x and r, therefore, the flow is essentially two dimensional here, because it depends on both x and r. If you further proceed along the tube, when you reach x equal to L subscript development or DEV, at this position the profile will become full. That means that the velocity will gradually vary from 0 at the wall to a maximum at the center, more like what is shown here. What I have shown here is typical of the velocity profile anywhere after this particular location. This velocity profile is valid from here onwards for x greater than L DEV. So, the velocity profile actually becomes a function only of the radius, and therefore, it is one time depends only on the radial coordinate. It does not vary with the location. So, we say that the velocity profile is now fully developed. The reason why we are looking at this is because after the development length x equal to x L DEV, beyond this the velocity profile does not change, and the velocity profile does not change. Therefore, there is no change in the momentum of the fluid as it crosses any cross section. The same momentum is crossing any section, and therefore, we can in fact prove from fluid mechanics principles that the friction is the friction which is at the wall, there is a friction, there is a shear stress. The shear due to friction is compensated by the pressure drop along the length of the tube. So, this is the basic reason why we are looking at it. It is also known from the fluid mechanics principles that the development length is given by 0.05 times the diameter of the tube times the Reynolds number based on the diameter of the tube. And if you remember recall the Reynolds number, it is nothing but the velocity times the diameter of the tube divided by the kinematic viscosity of the fluid. And for laminar flow to prevail, this Reynolds number must be less than some critical value, below which it will be laminar, and if it is above that, it will become transition, and then it of course will become fully turbulent if it is much larger. In laminar tube flow exists if the Reynolds number is less than about 2000, a little more than 2000, but for our purpose what we will do is we will assume that the laminar tube flow is guaranteed in an apparatus which is used for measurement of viscosity by requiring the Reynolds number to be smaller than the critical value. You can take for example a value like 500 or 1000 would be good enough for the experiment purposes. So, a laminar flow setup in a small diameter tube. So, a capillary is nothing but a small diameter tube. What I have to make sure in using the method which employs pressure drop in a tube of circular cross section is to maintain the Reynolds number less than the critical value. Of course, we do not know what is the viscosity, therefore, it is a priori it is difficult to find out what is the Reynolds number, because only when you measure the velocity and when you know the viscosity only we can find out. So, what we will do is we will assume that somehow we are able to maintain the velocity to a value such that for a given fluid whose viscosity we want to measure using this apparatus, the Reynolds number is less than the critical value. If it is not less than critical value, we will have to adjust the flow rate such that it comes below the critical value. So, this I will make it clear when we take up the example. So, what is required for the apparatus is very simple. I require a certain length of tube, I have to allow for developmental length, and the tube must be longer than the development length plus some length over which I am going to measure the pressure drop. So, I have taken a length equal to L development plus a subsequent value L across which I am going to measure the pressure drop. which is actually measured using a manometer connected between these two tappings here, one at the upstream side, one on the downstream side. And in this case I am showing a rotameter to measure the mass flow rate or the volumetric flow rate, and of course if you know what the volumetric flow rate is and divide by the area of cross section of the capillary tube, you can get the mean velocity of the flow. And if you remember, the Reynolds number is based on that mean velocity, which we calculate by taking the volumetric flow rate divided by the area of cross section of the tube. To the left of this rotameter, I have shown a constant head arrangement, because the flow will have to be maintained steady through this tube. That means that the pressure at which it is going to enter this length of tube must be constant, and therefore one way of doing it is to have an overhead tank at a suitable height, which can be changed by shifting it up or down as is required, and you supply through a pump water or whatever liquid we want to measure the viscosity of, that is circulated through this, and the excess fluid is going to drain back to the sump through an overflow arrangement. That means I can maintain this level constant. If this level is constant with respect to the level of the tube, there is a given head which is maintained for the flow of the liquid or the fluid through the capillary tube. So the volumetric flow rate is measured here, or if the volumetric flow rate is very small, as it happens in most applications of this type, you can actually collect the fluid as it comes out in a graduated jar and measure the volume collected over a certain period of time. A very simple and a very accurate method is to collect the fluid in a jar, very accurately graduated jar, and then measure the volume over a certain time interval, which can be measured using a stopwatch. And the head H indicated by the manometer gives you the delta P across the tube length L. So actually delta P divided by L gives you the pressure gradient, or the pressure gradient delta P by L. In fact, it can be shown that the pressure gradient is uniform when the flow is fully developed. When the flow is fully developed and the velocity does not change with respect to the axial location, the pressure drop per unit length is the same as the pressure gradient. Let us take a simple example, and through this example I am going to indicate how one goes about making the measurement of viscosity using a capillary tube, flow through a capillary tube. So the example 46 actually looks at viscosity of water is to be measured using laminar flow in a tube of circular cross section. We want to design a suitable setup for this purpose. So this will give us some idea about how to go about doing the measurement also. So let us look at the typical arrangement. So we want to, so this is nothing but example 46. Instead of the usual problem solving, I have taken a design problem, design of the setup, and I am taking water as the fluid or the liquid whose viscosity we want to measure. Water is the liquid, and let us assume that water is around room temperature. That means that the temperature is something like 25 degrees centigrade. So for design purpose, what I can do is I can take the properties of water roughly at this temperature and then design the setup for that particular condition. So if you look at a table of properties, the following are the approximate values I am not going to take exact values, because for the design purpose all you require is the value which is approximately equal to the value which we are going to measure in the experiment. We need not worry about a very precise value, we are going to just take the ballpark value or the closest to what we want. I can assume that rho is typically 1000 kg per meter cube. This is the density of water, and then the viscosity, which is the kinematic viscosity, nu is to about 10 to the power of minus 6 meter squares per second. I am not taking very accurate value, I am not taking any, it is not multiplied by something which is close to 1, I am just equal to 1, roughly 10 to the power of minus 6 meter square per second. And if you calculate the viscosity mu is nothing but nu times rho, which will be approximately, in fact I will use a symbol like this because it is just the approximate value I am using. This will be 10 to the power of minus 3 kg per meter second, that is the unit of viscosity. So we have now a fluid whose viscosity is given, and what I have to do is to look at the laminar flow is what is required, and let us assume that the Reynolds number based on the diameter is roughly 500. I do not want to exceed this value. If you have very low Reynolds number, the pressure drop will become very high. If you go to large Reynolds number, there is a danger that the flow may become turbulent in the experiment. Therefore, we have to go for some median value like this. So, I am just taking RED equal to 500 as a possible value. And let me also take a diameter of the tube, which is the inner diameter of the tube. I will take as a suitable value. In this case, I am going to take a 3 millimeter inner diameter tube. 3 millimeter is it is not a capillary in the strict sense of the term, but it is a small diameter tube. In fact, if you want, you can take even smaller tube. For example, with gases you may be able to take much smaller tubes to make the measurement. So, by definition, RED equal to 500, which is what I have taken, is the value V, which is the average velocity in the tube, multiplied by D by nu, and I will substitute the values V into 3 millimeters 0.003 divided by nu is 10 to the power of minus 3, minus 6, as we saw in the previous case. And therefore, this gives you a velocity of 500 into 10 to the power of minus 6 divided by 0.003, and this is roughly 0.167 meter per second, or this is 1.67 centimeter per second. So, I am talking of very small velocity of the water inside the tube. So, you must realize that the smaller the velocity of the water, the smaller the Reynolds number in this case. Okay. So, the idea is to have very small velocity in the tube. In fact, I can find out what is the corresponding quantity of flow Q. Q will be nothing but the velocity times the area of cross section of the pipe. So, we will say V into pi d squared by 4 and we can substitute. So, Q will be equal to V is 0.167 meter per second multiplied by pi multiplied by 0.003 whole squared by 4. This will be in meter cube per second, and this will come to a value equal to 1.178 into 10 to the power of minus 6 meter cube per second, which is the same as 1.178, which I will say roughly 1.2 milliliter per second. So, it is just a flow of 1.2 cubic centimeter per second, it is a very small flow rate. In fact, you can immediately see that I can use a graduated jar, which is used very often in the chemical laboratory. Very accurately graduated jars are available. All I have to do is to collect this water. For example, if I collect over 100 seconds, I will get about 120 cc will be collected. So I can perform the experiment for about 100 seconds, something like 2 minutes. I will be able to collect 120 milliliters, which can be very accurately measured. Therefore, the volumetric flow rate which I have got here is a accurately measurable quantity in this particular experiment. So that is what I am going to do. Next, let us see what is the length of the tube I would like to have. So the length of the tube, as you saw, length of tube should be greater than the L development plus L, the length over which I am going to measure the pressure drop. So the development length, the L development can be determined by using the development length formula I gave earlier. If you remember, L development is equal to 0.05 multiplied by the diameter, in this case 0.003, multiplied by Reynolds number, which is 500. So this is the length required for that. This is the length required for the development length in meters, and this has a value equal to 0.075 meters. So what about L? I would like to now make an assumption that I should be able to measure the pressure drop accurately. It should be large enough so that it can be measured with a suitable pressure drop measuring device. So I will assume that the pressure drop delta P is something like 1 kilopascal, which can be easily measured. Of course, if you choose a different value, you will have to use a different instrument for measuring the pressure drop. So depending on the magnitude. In fact, we can show from laminar flow theory, we can show very easily. All you have to do is the student has to refer to a book on fluid mechanics, and these equations are given there. We know that delta P by L, the pressure drop along a length L of the tube, is given by 32 nu V by d squared, where nu is the kinematic viscosity, V is the velocity, d is the diameter, delta P by L is given by this quantity. Therefore, now if you see, I have chosen delta P. I now already know this, I know the velocity, I know the diameter, so I can determine L. So this L which I am going to determine from this is the required length, so that you get a 1 kilopascal pressure drop across the length. So let me just do the calculation. So we can say that L will be equal to the formula has to be rearranged so that we solve for it. So delta P into d squared divided by 32 nu V, by rearranging that formula. Delta P is 1 kilopascal, is 10 to the power of 3, d squared is 0.003 whole squared divided by 32, nu is 10 to the power of minus 6, multiplied by V is 0.167. These are the values which you already determined. This will be so many meters, and if you work it out, it comes to 1.68 meters. Therefore, the tube length required is greater than 1.68 plus 0.075, something like 1.76 meters. Actually, one could choose a length of 2 meters, which is the standard length available from the manufacturer. 2 meters is the standard length, so you can take a 2 meter length of the tube. In fact, I can choose a tube made of copper, which is easily available in the market, or you can even go for some other material. Stainless steel can be obtained, 3 millimeter ID diameter tubes are available. So, I can use that. However, I have to make arrangement for the pressure taps at 1.68 or roughly 1.7 meters interval. I have to make the pressure drop measurement across that length, so that you get a value of delta P roughly equal to 1 kilopascal. So, the design of the experiment is very simple. Now, of course, you have to ask yourself the other question: how do I maintain the velocity in the tube equal to 0.167 centimeter per second? That is the value we obtained. We know what is the pressure drop in the length of the tube. This pressure drop must be available through the head available from the overhead tank. So, that is how you fix up the location of the constant head tank. So, the constant head tank must be at a certain level, such that the total head required for the flow to be maintained through the apparatus is equal to or greater than that, slightly greater, because there will be other extra pressure drops through the tubes which are going to come into the picture. So, you have to allow for that and find out what is the pressure drop required. Actually, that is not what we are going to do in practice. In practice, we now know what are the rough measurements, rough dimensions which are required. You just design around that. You do not have to actually take these numbers. You can take numbers very close to them, and by trial and error you can adjust the height of the tank, so that you get a flow rate of about 120 cc in 100 seconds. That is what we wanted, or 100 cc in 100 cc in 100 seconds, for example, 1 cc per second. That is all what we want. So, we can now adjust, having decided on the major dimensions of the apparatus, we can use the trial and error and fix up, such that the conditions which we wanted are indeed obtained in practice. The question is, suppose I am going to use a different liquid instead of water, what is going to happen? So, we may have to rearrange the head required, such that with a different liquid I still am able to get similar numbers, that is delta P roughly 1 kilopascal over a length of 1.7 meters and so on. That is how it is done. So, this gives you an idea as to how to use a capillary tube flowed laminar flow in a laminar tube flow in capillary tube flow to obtain the viscosity. In this case, I am obtaining the kinematic viscosity. Of course, if you need to know the density can be easily measured. All you have to do is to take a certain volume of the liquid in a graduated jar, measure the weight, weigh it separately, and knowing the volume and the weight or the mass, we can directly calculate the density. Therefore, the viscosity mu, the dynamic viscosity, can also be calculated once we have the value of the kinematic viscosity. By measuring the density separately, we can do that. This method, this tube flow, is also possible in the case of gases. In the case of gases, I cannot collect the gas as we have done in this particular case, even though collection of gas is also possible. We will not go into the details of that. We can use a rotometer and measure the volumetric flow rate, so that is available, the velocity of the flow is available. Then we measure the delta P just as we did here, but we may have to use a suitable manometer which will register the pressure drop, which may be smaller in the case of the gas. So, we may require a different manometer or a pressure measuring device to do the measurement, but the principle remains the same. I may in fact actually use a much smaller diameter tube in the case of gases, so that the pressure drop is substantial, and then of course I can make the measurement. So, the first method is the use of laminar flow in a tube, and the second one, let us look at the second method. The second method is also related to the flow through an orifice, but the capillary is here at the bottom of the vessel. The capillary is the bottom of the vessel, and you can see the schematic of the Seybold viscometer I have taken. This is actually taken from the book by Holman. The numbers given here are all taken from a standard dimensions for Seybold viscometer. Let me just give briefly the method or the principle of operation of this instrument. It basically has got a vessel which can hold a certain volume of the liquid whose viscosity I want to measure, and it is terminated at the bottom. There is a small capillary of a standard length equal to 1.225 centimeters and a standard diameter equal to 0.1765 centimeters. So, this is very important, these dimensions are important, and we have a mark on the jar or the receptacle which holds the liquid, and above this from up to the top of the brim of that vessel, the volume is exactly equal to 60 milliliters. So, what I am going to do is to take 60 milliliters here, and I want to allow this 60 milliliters to be drained through this capillary tube, and the time taken is a function of the viscosity of the liquid. And of course, in order to maintain the temperature of the entire apparatus at a constant value, I can have a constant temperature bath as is shown here. If you do not do anything, the temperature will be just the atmospheric temperature or the room temperature. If you have a constant temperature bath as is shown here, you can maintain the temperature at any particular value you want, so that the viscosity we measure will be a function of temperature, because most liquids show a tremendous variation of viscosity with respect to temperature. Therefore, if we are interested in measuring the viscosity as a function of temperature, we can vary the temperature of the constant temperature bath to suit the measurement required. So, you can see that the diameter of the vessel is 2.975 centimeters. These are accurate values. The Seybold viscometer is manufactured and sold, and it is all these numbers are from such a design. So, the entire length from here to here is 12.5 centimeters. So, all I have to do here is to fill the inner vessel up to the brim, and then start a stopwatch, and then allow the drainage up to this level, and then find out what is the time taken for this operation. So, the drainage time is related to the viscosity in a very somewhat complicated way, and the relationship is given actually in the slide here. So, the kinematic viscosity nu, this is not V, it is nu. Kinematic viscosity nu is given as a function of the time for drainage of 60 milliliters of the liquid through the viscometer. So, 0.302218 T minus 0.1793 divided by T multiplied by 10 to the power of minus 3 meter squared per second. This is the unit. So, the kinematic viscosity is a function of the time for drainage. So, let us look at a typical example. I have used a Seybold viscometer. It is used to measure, this is example 47, it is used to measure the viscosity of engine oil. Engine oil is used in applications like IC engines and so on, in compressors, wherever we want to reduce the effect of friction. Lubrication requires engine oil. So, we are talking about a lubricating oil here, and the time recorded for discharging 60 millimeters is given as 215 plus or minus 0.8 second. This is the experimental uncertainty, 0.8 second is the uncertainty. So, we want to calculate the kinematic viscosity and also determine the uncertainty. So, I will work it out on the board as usual. So, this is example number 47. It is simple application of that formula. So, if you ask me how we got the formula is obtained by making measurements with liquids whose viscosity has been determined by some other method or is available from handbook or has been measured by other people very accurately. So, use standard reference liquids whose viscosities are known, and then or use a standard reference liquid whose viscosity is accurately known as a function of temperature, and allow it to be used in this particular apparatus, measure the times for the various temperatures corresponding to the various values of viscosity the liquid will have, and then try to fit the data using a curve fit procedure, which is what we have done earlier in our earlier lectures. So, the curve fit is actually what is giving this particular relationship. Okay. So, the relationship between the drainage time, of course drainage time is dependent on two things. The height of the liquid is given, it starts at with the maximum height and then it starts coming down. Therefore, the time is precisely determined by the head available. At any instant of time certain amount of head is available. and there is a friction, the resistance to motion through the capillary is there. Therefore, it is determined by a complicated relationship between the head and the speed with which it is going to move through the nozzle or the capillary tube, and the time is therefore related to the viscosity of the liquid, and that is how the relationship has been obtained. Now, in this example I have given that in the case of some oil, the time measured was is given as 215 plus or minus 0.8 seconds. So, this is the time, and all I have to do is to substitute in the expression which I gave earlier, nu is equal to 0.22018 into 10 to the power of minus 6 into 215, that is the time, plus minus 0.1793 into 10 to the power of minus 3. What I have done is that 10 to the power of minus 3 outside the formula has been taken inside, divided by 215 again, so many meters squared per second. So, it is a very simple and straightforward problem. So, this comes to 46.5 into 10 to the power of minus 6 meters squared per second. This is the kinematic viscosity of the oil sample. Now, I want to determine, because of the uncertainty in the time measurement, what is the uncertainty in this one. So, for that I have to do what I have to do is to find out the derivative of nu with respect to time. So, d nu by dt will be, this is actually t, this is also t. So, if you take the derivative, it becomes 0.22018 in 10 to the power of minus 6, first term. The next term will give you plus 0.1793 into 10 to the power of minus 3 divided by t squared. T squared is 215 squared. This is the derivative of nu with respect to time. This will be in meter squared per second squared, nu by t. So, this is a very simple problem. We can say that delta nu by nu is nothing but d nu by dt into dt by nu. This is the uncertainty in the nu value. This is the derivative I obtained, multiplied by delta t. If you want, you can show it as delta t here. So, I can write it as so, it just requires the value of the derivative to be determined, and it is given by plus or minus, because delta t is plus or minus 0.8 divided by nu is determined earlier 46.5 in 10 to the power of minus 6 into 0.22018 in 10 to the power of minus 6 plus 0.1793 10 to the power of minus 3 divided by 215 squared. This gives you a value of, if you multiply by 100, of course you will give percentages, so it gives plus or minus 0.47%. So, you can see that the plus or minus 0.8 second in the drainage time which is measured, the uncertainty in the drainage time which is measured of 0.8 seconds plus or minus 0.8 seconds gives rise to almost a 0.5% uncertainty in the viscosity. This is not very bad at all. If you remember, in the case of thermal conductivity and other methods, other properties, we are talking about 5% or thereabouts. We are now getting much better numbers. Plus or minus 0.5% is a very good measurement given the importance of the particular quantity we are measuring. Therefore, this gives a very simple example of how to use the Seybold viscometer. Seybold viscometer is named after the person who invented the viscometer, and it is standardized. Actually, according to ASTM and ASME, this is one of the standard methods which is specified, and in fact the standard reference materials are also mentioned for the measurement purposes. What I have done is to make a simple plot showing what would happen if I were to use SAE20 unused engine oil. This is a lubricant of a relatively low viscosity, SAE20, and all I have done is taken the data for engine oil, which is in the form of temperature versus viscosity or the kinematic viscosity, and I have used it in the Seebold viscometer by using a thought experiment, and I want to find out what will be the drainage time which is measured in the experiment if it were performed. So, if I vary the temperature from 0 to 160 degrees Celsius, the time for drainage, you see for here it is about almost 3000 seconds. It is going to take about at 0 degrees Celsius, this SAE20 engine oil, 60 milliliters will come out of that Seebold viscometer in almost 1 hour it is going to take, and of course you can measure that time very accurately. Suppose you go to some place like 25-30 degrees, which is the room temperature value, you see you still have already about 500 to 600 seconds, which is about quarter hour, 15 to 20 minutes. And when you go to very high temperatures, you see that it is very fast drainage. Viscosity is a decreasing function of temperature. As you heat up the oil, the viscosity comes down tremendously, and you can see that at this particular position it drains out within about 20 to 30 seconds. The point I want to make here is that for most liquids whose viscosity we want to measure using Seebold viscometer, the drainage time is measurable and very accurately measurable, because it varies from about 1000, 3000 to about 50 or 20, 25 or 30, which is easily measurable, accurately measurable. That is a very important thing, and therefore, in other words, it means that this Seebold viscometer can be used for large range of values of viscosity of the liquids. The third method I am going to look at is a rotating concentric cylinder apparatus. Let me try to explain how this works physically, and then we will try to work out a formula which will give the desired quantity. So, the apparatus actually consists of a stator or a stationary cylinder, which is supported here. This is a support. So, this is stationary cylinder, and there is a rotating cylinder, and between the stationary cylinder and the rotating cylinder there is a small gap B. Of course, at the bottom also there is a small gap A, and this outer cylinder is rotated at a constant rotational speed omega. So, the white patch here is actually the liquid film, which is this liquid film which is marked here as this white region in between the outer cylinder and the inner cylinder. So, let us see what is going to happen. Suppose as I rotate the outer cylinder, the film of liquid which is in between the two cylinders is going to undergo a shear, because the velocity of the outer cylinder is radius times the omega, and the inner cylinder is held fixed. Therefore, there is 0 velocity at the inner cylinder, edge of the inner cylinder, and there is a maximum velocity at this place, and if the gap is narrow, we can show actually that the velocity profile is linear. That means that the velocity varies from 0 to the maximum in a linear fashion. When you have linear velocity profile, the shear stress is a constant, because shear stress tau is equal to mu du by dy. If du by dy is equal to a constant because linear, that means that tau is proportional to mu. So, there is a shear stress which is a constant shear stress which is going to be experienced by the stationary cylinder. Of course, the same shear stress will also be experienced by the outer cylinder in the opposite direction. Now, the point is, if you see here the small diameter place here as far as the stationary cylinder is concerned, suppose I measure the stress, torsional stress developed or the shear stress developed by this one by putting a load cell on the circumference of that is going to measure a stress which is proportional to the torque, and that torque is related to the viscosity of the liquid, which is going to be in this gap, the gap here as well as here. This is equal to length equal to L. I think this is missing. This is length is L, so you make it as L. This is V and this is A. So the what we are measuring is the shear stress, which is related to the torque, and the torque is measured by using the stress, which is or strain measured by a load cell. The load cell is going to measure a strain. That strain is proportional to the shear stress, that is in turn is proportional to the torque. So we can calibrate by suitable means. So the torque is measured, and the torque is measured and related to the viscosity of the liquid, which is in the white region shown here. So for determining what is the torque, let me try to derive the suitable relationship. So what I have essentially is an inner cylinder and an outer cylinder. I am just making the sketch here. This is the, let us say this is R1 and this is R2. This is the center line of the. So the gap B is nothing but R2 minus R1. The difference between the outer radius, inner radius of the outer cylinder and the outer radius of the inner cylinder, that is R2 minus R1 is the gap B, and of course at the bottom I got a B gap equal to A. The outer cylinder is rotating. So what is the velocity? Because of rotation, the velocity will be nothing but R2 times omega. That is the surface speed, and the velocity here is 0. So if I throw the gap here, this is R1 and this is R2, I have the velocity equal to R2 omega, and the velocity is like this. This is 0 and it is equal to R2 omega. Because of this velocity gradient, which is of course uniform, there will be a shear stress tau. I am looking at this length equal to L, this length equal to L. Over this length, a uniform shear stress is going to be given by mu du by dy, which is nothing but mu times du by dy is nothing but this height divided by this R2 omega by B. Now the shear stress can also be written as the torque divided by the radius arm, tau is equal to divided by, this will be a force, torque divided by the radius is going to give you a force. This force divided by the area, which is nothing but 2 pi into R1 into L, gives the stress. Therefore the shear stress is nothing but T1 by R1 divided by 2 pi R1L equal to mu du by dy, which is equal to mu R2 omega by B. So this gives you a torque equal to T1. From here I can work out a torque equal to T1, and it can be written as torque. So T1 is equal to 2 pi mu R1 squared R2 L omega divided by B. We will call this as expression number 1. Now let us look at the torque due to the film which is at the bottom of the cylinder. So if I draw the bottom of the cylinder, so this is the axis and there is a gap of A, and at any location at a radius equal to R, this part is moving, this part is stationary. This is moving with velocity equal to omega times r, and this is 0 velocity. So, if I look at the velocity gradient there, velocity field there, I can show it like this. This is 0, this is omega r, and the velocity will show a linear variation like this. Therefore, the corresponding to this, we have a shear stress which is a function of r, which is given by this r omega is the velocity divided by the gap which is a multiplied by mu r omega by a. And this shear stress, we can assume that you can take a small length over which this is the value of shear stress, delta r we can say, or dr. So, we can make it dr. So, what is the area over which it occurs? Area as a function of r given by 2 pi r dr. Therefore, this is like a shear force or a force equal to tau into a, which will give you 2 pi omega mu by a multiplied by r squared dr. And this is going to give rise to a torque. So, we will call it the elemental torque. You have to multiply by another factor of r. Therefore, 2 pi omega mu by a into r cube dr. So, what I have to do is now to calculate the total torque due to this elemental torque. Therefore, 2 pi omega mu by a into r cube dr. So, what I have to do is now to calculate the total torque. Let me just verify the expression in the previous page. This is expression 1, 2 mu pi r1 squared r2 L by b 2. So, the total torque which is measured by the measured will be equal to T equal to T1 plus T2. Mu is common for both the expressions. So, it will be mu multiplied by 2 pi omega r1 squared r2 L divided by b plus omega pi r1 to the power of 4 divided by 2a. So, we can call it expression 3, and you see that T is equal to, this is measured, all these quantities inside this bracket are measurable. Omega is the speed which can be measured, r1, r2, L are all the geometric parameters describing the apparatus. Therefore, I can solve for mu. So, mu will be nothing but the torque measured divided by the geometric parameters and the speed parameter omega, which is also measured. Therefore, we can write the final expression as the viscosity mu is equal to total T divided by pi omega r1 squared divided by r1 squared by 2a plus 2r2L by b. So, this is the final expression I am going to get, which we will call it expression 4. So, in the next lecture, we will begin the lecture by taking an example which will demonstrate the use of this particular technique for the measurement of viscosity. Thank you.